MergeSort is the simplest, most symmetric sorting algorithm there is. And yet I know people who have hated algorithms all their lives because the way they were taught MergeSort. Today we are going to learn about MergeSort and its time complexity, and I promise we will not hate it. Here I have filled the screen with an example of MergeSort. We start with an unsorted list, and at the end we have it sorted. In all honesty, this last step is where like the 90% of work is done. And if we understand this, then we're practically good to go. So let's zoom in on this step. If you look carefully, we have two already sorted lists, and we combine them into one. And the way we do it is quite simple. We compare the topmost elements of the lists and move the smaller one to the new list. We pick the top two elements, compare, and move the smaller element to the new list, and repeat. Pick top elements, compare, move smaller elements. Keep doing it until one of the lists is empty. At that point, we simply move the remaining guys to the new list as well. The way I visualize this, it's a wrestling match, like those Japanese sumo wrestlings with two teams. Each team sends a champion to the arena or the ring, and as always happens, the heavier, beefy Hulk always wins and knocks out the skinny fellow. The losing team sends a new guy. The heavier of the two wins again. This keeps on going until one of the team runs out of players. At that point, the match is decided, and all remaining players of the winning team go back to the pavilion too. Can you figure out how many wrestlings take place at max if both teams have 6 players each? Here is an easy way to count them. In each game, one player must lose, right? And everyone loses at most once. So there are exactly as many wrestlings as there are losers. At max, how many players must lose? There must be one winner at the end, right? So the maximum number of losers is at most 11. And hence the number of wrestlings can't be more than 11. In general, if you have two teams of n over 2 players each, the total number of wrestlings or the comparisons is at most n minus 1. Great! We now know what happens in this last step, and we know that this merge step takes order and time. But where do these already sorted lists come from? Well, the first list comes from applying the same merge step on two even smaller lists in the previous step. And so does the other. So exact same merging is taking place in the previous step of the algorithm. And the step before that. And the step before, until we have lists that only contain one element each. So the second half of the MergeSort algorithm is just a repeated application of the merge algorithm or the wrestling tournament that we just saw. Well, what's going on in the first half? We just prepare the lists, aka divide them into smaller parts for the merge steps. We divide each list into 2 equal halves, or almost equal when the lists contain an odd number, In that case, we will have one half which contains one element more than the other, but that does not affect anything at all. We divide again and again and again until, that's right, until we have lists with exactly one element each. And then lists are ready for the combine or the merge step. The neat part is, when doing it recursively, you just need to make 2 recursive calls and then call the merge step. Everything else is taken care of. Just provide a stopping condition of when you want to stop the dividing. We, of course, want to stop when the lists have exactly one element. That is the whole of MergeSort algorithm. The first half is dividing the list into 2 parts, and the second half is a sumo wrestling match where beefy guys always win, as they usually do in life. Neat, isn't it? An important part of an algorithm is the analysis of its runtime. If your algorithm is a recursive one, as is the case with MergeSort, you can write your runtime as a recurrence and then solve it. Recurrence for MergeSort is quite easy. Let's say our algorithm takes some t of n time on a list of n, then step 2 and similarly step 3, which calls the same algorithm on n over 2 elements, must take t of n over 2 time. We already know that the maximum number of wrestlings in the merge step is just the number of elements in A plus the number of elements in B minus 1. So that cost is at most a constant times n. That's your recurrence. And it solves to a constant times n log n. I have a separate video on how to solve this recurrence, which I'll link here. But the reason this solves to n log n can be guessed from the coefficients of the recursive calls. Particularly important is the fact that these coefficients add up to exactly 1. If they had added up to less than 1, then our total time would have been just order n. And if they had added up to anything more than 1, then our total time complexity would have been strictly bigger than order n log n. Can you guess what would be the solution to the following recurrence? Happy thinking!